Okay, so Unit 6, continuity. Okay, so in Unit 5 we saw limits of functions that are the behavior of a function when it gets close to one particular value, right? Um, there are some types of functions in which the limit uh, of the function when it gets to a point is exactly the value of the function at that point, and that's continuous functions, okay, which are in an intuitive sense those functions that you can draw, with from without getting the pencil out of the paper, okay, or the chalk out of the blackboard, right? This is a very intuitive sense that is formalized by these concepts that we will see now. Continuous functions are super important in analysis, in calculus in general. Most of the things that we will do will deal with continuous functions, and they have a lot of interesting properties that allow us to say many more things. Okay, so the definition of continuity, or a function that's continuous, a function f is continuous at a point a in the domain if the limit when x goes to a of f of x is f of a, okay, what I just said. And this definition can be restricted to intervals, to subsets of the domain, okay? A function doesn't have to be domain continuous in all of its domain. It could be continuous in only intervals, okay? So it could be that f is continuous in this interval open a b if it's continuous for every point of x in that interval, okay? If that equality, the limit when x goes to a of f of x equals f of a, is valid for every point in this domain, right? So and that's also true for all these different intervals, right? Examples of continuous functions are polynomials, as we saw in last video. The limit when x goes to a of a polynomial is the value of the polynomial at a. Rational functions, right? Whenever the denominator is not zero, okay, so in their domain they're continuous. As we saw, also the sine of x and the cosine of x are also continuous. The tangent of x, because it's a fraction of continuous functions, it's also continuous, except when it's not defined, right? Except in the parts or the multiples of pi over 2 where it's an asymptote, right? Also with a cotangent. Okay, so let's see a proof of some other continuity functions. So let's see that the exponential e to the x is a continuous function. Okay, so in order to do that, we have to prove that the limit when x goes to a of e to the x is e to the a. Is this true? Well, we can always write e to the x as e to the x and then multiply by e to the a e to the minus a, right? Or in other words, we can say this is e to the a times e to the x minus a, right? Now if we compute the limit when x goes to a of e to the x, this is the same as the limit when x goes to a of this expression, e to the a times e to the x minus a, and so this is e to the a times the limit when x goes to a of e to the x minus a. Now we know that this thing is equal, e to the x minus a minus 1 is asymptotically equivalent to x minus a whenever x minus a is small. So in other words, this is wait a minute. Yeah, so this is asymptotically equivalent to this 1 plus x minus a, right? So we can substitute here. We have let's see, this is e to the a times the limit of this expression when x goes to a, so this is times 1 plus a minus a, and this cancel out. This is 1, so this is e to the a, which is what we wanted to prove. So that means that the exponential function is continuous. Okay. Okay. Now let's see. Using the properties of the limits that we saw in last unit, we can prove many properties of continuous functions, or many algebraic properties that we can use, and that will be useful for later. Okay, so if we have two functions f and g that are continuous at some point a, then the sum and the multiplication of those functions are also continuous at that point. And if g of a is different than 0, then the division between f and g is also continuous at a. Okay. Then if g is continuous at a and f is continuous at g of a, then f composed with g is continuous at a. And this stems directly from the definition of the limit of composed functions that we saw last unit. And then if an invertible function f is continuous at a, then f minus 1 will be continuous at f of a. Okay, which implies that the logarithm is continuous in its domain in 0 infinity, because ex is continuous in R. Okay. We can also say, the arc cosine, the arc sine, all of these inverse functions that we have seen are continuous because their inverses are continuous. Okay. Now we can say, let's see if we can use some of these properties to prove that the function f of x, x to the alpha, where alpha is a real number, is continuous in 0 infinity. Okay. Well, we can always, and this is an important point, whenever we have a power of x, we can always write it like this. This is e to the alpha logarithm of x. Okay, and this is actually the definition of the power of x. So x to the something is actually defined like this. Okay, or you can go from this to this. Okay, for alphas that are not natural or rational. Sorry. Okay, so now if this is true, then this is the composition of e with this function, the logarithm of x, alpha logarithm of x. Both functions are continuous, so that means that this is continuous. Okay. Now what happens at 0? Okay, x equals 0. We have to define that f at 0 is 0. Okay, 0 to the alpha is 0. Okay, then this is also continuous at 0, because the limit when x goes to 0 on the right of x to the alpha, which is the same as the limit when x goes to 0 on the right of e to the alpha logarithm of x. Well, this is e to the alpha limit when x goes to plus 0 from the right of the logarithm of x, but this is minus infinity, or in other words, so that means that this is e to the minus infinity, which is 0. Okay, so this is the same. We could do it by changing the variable and saying t is the logarithm of x, so the limit when x goes to 0 on the right is the same as the limit when t goes to minus infinity. Okay, you could also say this. And so what happens if alpha is this is valid, that it's continuous in 0 infinity if alpha is greater than 0, otherwise it's not defined, right, at 0. And if alpha is 0, right, f of x is 1 in 0 infinity, and we can define f of 0 equals 1. If we define it like that, so 0 to the 0 is 1, then we can say that the function is continuous in this closed infinite interval. Okay. Now, sometimes these functions, our functions are not going to be continuous, and they're going to be discontinuous at some points. That means that the limit when so the limit when x goes to a of f of x is not going to be equal to f of a. Okay, or if a is not in the domain, it could be the case that the limit when x goes to a from the right is not the same as the limit when x goes to a on the left. Okay. So for instance, let's see, we have f of x sine of x over x, right? So this function is continuous in all points except 0, right? Because 0 is not in the domain. But what happens at 0? Well, the limit when x goes to 0 of the sine of x over x, we know it's 1, right? So if we define this function g of x as the sine of x over x when x is different than 0 and 1 when x is 0, then now we have a function that's continuous in the whole of the real line, right? So we have took a function that's not continuous at one point because it's not defined there, and kind of like put a point there, and with that we have kind of completed the function and made it continuous. Okay, when that's the case, we have what we call let's call them avoidable discontinuities. Okay, and that's discontinuities in which you have like something like this, a function like this, and then it has a hole here. It's not, this is not this function, okay, any other function, and this in here, the function f, this is f is not defined here. Okay, so if when that's the case, we can redefine a new function g, which is f in every point except in this hole, and then the value of the limit at this point, and then that new function will be continuous, and that's why what we call it avoidable discontinuities. Okay, let's see another kind of discontinuity. We have, for instance, the Heaviside function that we have seen, okay, which is 0 if x is smaller than 0, 1 if x is greater or equal than 0, right? Now this is the function that it goes like this, and then boom, right? And it does a jump, right? At 0, it goes from 0 to 1, and here we can't avoid it, right? There's no way we can define something at 0 with, you know, for instance, a value of 1/2 for the Heaviside function. It won't make it continuous because the limit from the right, you know, when you go to 0 from the right, and the limit from the left will never be the same, right? In this case, we call them jump discontinuities, okay? Because that's what the function does. It jumps from one value to the other, okay? And that's when the limit on the left and the limit on the right from one value is not the same, okay? And the last type of discontinuity are what we call singularities, which are points where the function is not defined, and it's not only a jump, it's that it goes to infinity, okay? The classical example for this is 1 over x, as we have seen, okay? The limit when x goes to 0 from the right of 1 over x is plus infinity. The limit when x goes to 0 from the left of 1 over x is minus infinity, okay? It's not only that there's a jump here, it's that the limit is infinite, Okay, it could also be the case that if you have, for instance, 1 over the absolute of value of x, you have this thing, right? It also goes to infinity in both cases, right? This is also a case of a singularity, right? Because at 0 it's not defined. Okay, so that's the 3 possible values of discontinuities, and well, also the fourth case, but this is less common, is that there is no limit at x equals a. So, for instance, as we have seen, the limit of the sine of 1 over x, well, the limit when x goes to 0 of this doesn't exist, right? We have seen, because this function does something like this and then starts to oscillate a lot, and then so this is 0, right? And it keeps oscillating, but around 0 it goes like this. Yeah, the oscillations increase in frequency further and further, so there's no limit there. Okay, so in that case, what we have is a different kind of discontinuity, because there's no limit. Okay, so related to this, there's this exercise, that I gave you this function f of x is x times the sine of 1 over x, and I ask you what kind of discontinuity has this function at 0. Okay, this function is not defined at 0, right? Because the sine of 1 over x is not defined at 0. What is the discontinuity? What kind of discontinuity of the 4 types that we have seen before? Okay, and now for the last part of the unit, we're going to see some theorems that are related to continuous functions that are defined in in closed intervals. Okay, if we have a function f in a closed interval, which is a very restricting property, many functions don't fulfill this, but if you have this, we can know a lot of other things about this function that actually allow us to prove many interesting results. Okay, the first one, and I guess the most important one from these results, is Bolzano's theorem, that I guess most of you have seen in high school. It says that if f is continuous in this closed interval a, b, and the f of a and f of b is smaller than 0, which means that the signs of the function f at a and b are different, then there is a value c in this interval, such that f of c, if c is 0, okay, which is kind of intuitive, right? You have a function like this, and then let's suppose we have the value at a is going to be positive, for instance, and the value at b is going to be negative. Well, if the function is continuous, that means we can draw it without raising our pen from the paper, and at some point it's going to cross the x-axis, right? It also is the same if f is negative at a and positive at b, right? But actually proving this, it's actually very interesting and not so easy when you think about it than this intuitive idea, right? The first corollary, and one of the most important corollaries from Bolzano's theorem, is the intermediate values theorem, which says that if we have a function f that is continuous in this closed interval a, b, and that we have a value z, right, that is between the minimum of f of a and b f of b, and between the maximum of f of a and f of b, then there is a value in this interval, such that the mapped value of f at c is going to be z. Okay, in other words, what this says is that f is going to go over every value between f of a here and f of b, every real value here that's in this interval. Okay, in this case, this interval, well, in this case, or the other way around, because f of b is smaller than f of a, right? The image of our function the image of f in this closed interval a, b is going to be is a subset of, or also not such subset, it's going to contain this interval. Okay, this means that every value between the extremes is going to be covered. Okay, and the proof of this is very simple, because we need to apply Bolzano's theorem. We define this function g of x is f of x minus z, right? And it's continuous because it's the sum of two continuous functions. And so suppose that z is between f of b and f of a and f of b, right? It could also be the case that if f of a is greater than f of b, these two guys are changed, but it's the same thing nonetheless, right? Well, then if we have we subtract f of x in both sides, right? So we have f of a minus f of x smaller than z minus f of x smaller than f of b minus f of x, right? Now, and we change the let's see, well, yeah, no, don't worry about this, it's not important. The idea is that if z is between these two guys, right, we have g of a is f of a minus z, which is smaller than 0, right, because z is greater than f of a, and g of b is f of b minus z, which is greater than 0. Okay, and if f of a and f of b change values, this is going to change direction, right? But in both cases we have that g of a has one sign and g of b has another sign. Okay, well, applying Bolzano's theorem, it says that g has to cross the x-axis at some point between a and b. Okay, so there's a value c, such that g of c is 0. In other words, that f of c is equal to z, which proves the theorem. Okay, so an application of this, okay, is that, for instance, if I tell you that this, if I give you this equation, okay, and I want to find roots for this equation, well, we don't know how to solve this algebraically, we can do it numerically, and you'll learn how to do it in the future, but we can use this intermediate values theorem to prove that this is going to have a solution that's positive. Okay, so let's call g of x is x e to the x minus 1, right? Well, let's call it x e to the x, right? Now, g at 0 is 0, right? And then g at 1 is e, right? Now, 1 is in this interval 0, e, right? Is smaller than e and greater than 0, right? So according to the intermediate values theorem, there is a solution for this equation in this interval, okay? In 0, 1, okay? Well, it's not 0, 1, it's in open 0, 1, right? Because 0 and 1 do not fulfill this equation, right? Do you see how to do this? And now the last important result, it's kind of similar, is that if f is a continuous function in this interval a closed ab, then we have a maximum value and a minimum value in this interval, such that there's an x sub small m, x sub capital M, such that their mapped values are maximum or minimum. Okay, so if we have our function a b, right, this is f of a, this is something like this, and then f of b, right? Well, what this says is that there's a minimum, there's a value here, right, xm, and there's a value, let's call it here, for instance, x capital M, such that they are the smallest mapped value, and the smallest f of x small m is going to be smaller or equal than f of x for all x in the interval, and this is going to be smaller or equal than x of capital M for all x in this interval. Okay, So that means that for a continuous function in a closed interval, it's going to reach an greatest and smaller value, or a minimum and a maximum. Okay, and in order to see how important it is, get for instance this function 1 over x, right? We have, suppose we're thinking about this function minus 1 1. Okay, well, this function is not continuous, right? Because at 0 there's a singularity, an asymptote. So that means that this theorem cannot be applied in it. It doesn't have a maximum or a minimum. It's not even bounded, right? This function close to 0, it's going to go to plus and minus infinity. So any value that we can think of as the maximum and minimum is going to be discarded, right? So that's important, that the function has to be continuous. And also, if we think about the closed interval, and that's a very important aspect, think about, for instance, the function f of x is x squared in this closed open 0 1, right? Now the function is continuous in this interval, this whole interval. What's the maximum, right? Whatever we think about, if we think about any value f of 1 minus epsilon, it's going to be 1 squared plus epsilon squared minus 2 epsilon, right? This is going to be smaller than 1. So if we choose, for instance, f of 1 minus epsilon divided by 2, this is 1 plus epsilon over 2 squared minus epsilon. Okay, this is going to be greater than this. Okay, so if we keep getting closer and closer and closer to 1, we keep increasing the function, because the function is increasing up until it gets to 1, right? So the supremum of this the values f of x, right, such that x is between 0 and 1. If you take this set, the supremum of this set is 1, right? That's an upper bound of all of these values, and that's the smallest upper bound. But 1 is not in the interval. Okay, it's not a map value of any of those values. Okay, so that's important. In order for these theorems to be true, f has to be continuous and it has to be defined in this closed interval. Okay, and that's the end of the lesson.